Thanks very much, everyone, for joining this afternoon, either via Zoom or on YouTube. And welcome to this 2021 British Astronomical Association Deep Sky Section meeting. Our annual, well, would have been our annual meeting this around about this time of year. And we had to cancel last year's, of course, in Sheffield, which was unfortunate. But certainly very pleased to be able to at least hold some sort of meeting this year, albeit in webinar format. We, of course, we normally have a full day's meeting in our annual meeting, and suppose slightly curtailed to just 2 speakers this year, I'm afraid. But I'm very pleased that we've got Dr. John Lightfoot from the Royal Observatory Edinburgh to speak to us this afternoon, and also Peter Goodhue, one of our BAA members, who's been specialising in imaging of planetary nebulae. So I think it'll be a really interesting programme of talks this afternoon. I think without much further ado, I should just pass over to John, who's going to talk to us about Hubble's Variable Nebula. Variable Nebula, of course, has been an interest of the Deep Sky section over many years, and is something which members have followed up on observations of for quite a while. So I think it'll be really good to get the professionals' view of observations of this nebula. So I'll pass over to John and let him give his presentation.
Thank you, Callum, for the introduction, and thanks for inviting me to give this talk. I'm not entirely sure that it's the professional view that you'll be getting, because I think variable nebulae, anything that sort of really changes within a few hours in the sky, is not something that professional astronomy is very good at looking at, certainly not in terms of variable nebulae. Anyway, I'll try and share my screen. Get to the start of my talk. Can people see that?
Yep, that looks great, John.
Okay, good. Okay, so I'm going to be talking about one particular variable nebula, probably the most famous one, Hubble's Variable Nebula. My name's John Lightfoot. I work at the UK Astronomy Technology Centre, which is actually part of the Royal Observatory Edinburgh, which is a fine Victorian building photographed here on a sunny day in Scotland. So I'm going to start in the middle of things, really. I can't actually remember when I first heard about Hubble's Variable Nebula. It's not something I ever learned about as an undergraduate. I suspect I was spending a sort of lazy afternoon on a Friday in UCL, University College London's library, looking at Aviation Week and Sky and Telescope and stuff, when I should have been working, looking through articles, and read an article about it. And I could well have seen this photograph in that article. This is quite a famous photograph. It's the first light photograph for the Mount Palomar 200-inch telescope, which was taken in 1949. And it actually marks the sort of brief meeting of, or the first meeting of 2 giants of 20th century astronomy. And really what's happening is encoded in the code written on the plate, which is given at the top there, PH-1-H. PH means Palomar Hale, which is the name given to the 200-inch telescope. Number 1 is, this is plate number 1, photograph number 1, and H is for Hubble, who was the observer, Edwin Hubble. So when I was growing up in the 1970s, the 200-inch telescope was the biggest optical telescope in the world, and had been for a couple of decades, and was still going to be largest working telescope for some time. And Hubble was probably, even then, one of the most famous astronomers in the world. So here they are. This is Hubble himself, affecting the appearance of a British gent, which apparently he picked up when he was in Oxford. And this is rather a nice drawing of the 200-inch telescope done in 1936, I think it says, well before the telescope was actually constructed, but obviously had been designed. The telescope, the dome is rather a sketchy sort of invention, I think, but the telescope is quite an accurate drawing. So, why did Hubble choose this particular nebula, of all the things he'd become famous for studying, to take the first photograph with the biggest telescope in the world? Well, so I've got quite a long history, really, because it's quite a bright object. It was known of by William Herschel. Someone called Schmidt in Athens in 1877 reported that he noticed that R Monocerotis, which is the star at the apex of Hubble's Variable Nebula, was a variable. And he got its classification NGC 2261 in the New General Catalogue in 1888. And then something quite sort of interesting happened in 1915, which is slightly earlier than I had realized the story of the actual variability of the nebula itself started. And I only discovered it this week, really. Hubble did his graduate studies at Yerkes Observatory near Chicago, and I think started in 1915 or 1916. At about the same time, a young man called John Edward Mellish was taken on as an amateur astronomer working at Yerkes as a sort of night, as someone who actually used the telescopes. Because apparently the director of Yerkes was having trouble attracting graduates. And Mellish was already quite noted as sort of a boy genius who had grown up on a farm in Wisconsin and ground his own mirror and made his own telescope and discovered a comet sort of thing. And he was taken on at the observatory, and he reported a comet. He noticed something in the sky which had changed between 2 or 3 visits, 2 or 3 observations, and he reported it as a comet. And this was duly reported by the Yerkes Observatory to the world, but had to be withdrawn because someone pointed out that it was actually NGC 2261. So there was a bit of, it sounds like there was a bit of a fuss at the observatory because they were embarrassed at having reported a comet which wasn't a comet. And Mellish was basically not given the job of investigating it further, even though he discovered its variability and must have maintained that it was varying. That job of investigation was given to Edwin Hubble, who was then a sort of young unknown student himself. And this telescope here, I think, is the telescope that Hubble used to do his studies of the variable nebula in 1915, 1916. And he confirmed that it was varying. He didn't just use his own observations, he used those of other people at Yerkes in America and even in Great Britain. And this is a series of 3 plates taken from his paper in the Astrophysical Journal in 1916, which was I think his first notable published paper, perhaps his first published paper. And these 3 plates, you know, the nebula does look quite different in them. I'm not quite sure that they're showing variability in the nebula or variability in the photographic emulsion of the plates. But anyway, Hubble saw enough to convince him that the nebula was varying. So that was his first encounter with the nebula, and throughout the rest of his life, he apparently maintained a strong interest in it and would observe it fairly frequently at regular intervals. Then another person enters the story, a guy called Carl Lampland, who spent his entire working life at Lowell Observatory in Flagstaff in Arizona. And Flagstaff Observatory was built by Percival Lowell to try and confirm the existence of canals on Mars. But half the world believed him, or wanted to believe him, and half the world didn't. And in an effort to try and get that unbelieving half converted, he thought it would be great. He needed photographs taken of the Canals of Mars. So Carl Lampland was taken on as a young man with technical expertise to actually get photographs, convincing photographs of Mars, the Martian canals. So in 1905 alone, he took 700 photographs of Mars. But throughout his career in Flagstaff, he also took nearly 1,000 photographs of 2261, the Variable Nebula, because I think he must have really caught his interest as a young man. So here are some old drawings of the Canals of Mars. Here's one of Lampland's photographs of Mars, which he took in 1907. And I've looked at these photographs, and they're actually rather, well, I've not looked at them. I've seen a couple of them on the web, Wikipedia, and they're actually rather impressive. I think they're pretty much as good as anything I saw on Sky at Night in the early 1970s with Patrick Moore. And it's funny that you can sort of convince yourself that you can almost see canals on some of them, but other times you can't. It's just like, you know, there's really no progress. And it didn't work out for Percival Lowell because these photographs were actually rather tiny and couldn't be reproduced well in the sort of magazines of the time. And over here is what's left of the telescope that Carl Lampland used. I think the only bit left is the telescope tube by the look of it. The mounting looks like it's made out of plywood, and the mirror was destroyed in some sort of hideous modification accident in the 1960s. So what I'm going to show now is a film made by a chap called Richard Hall, also in Arizona, in the 1960s, who put together a cinefilm of many of the photographic plates taken by Lampland from 1916 to 1951. The film lasts about 10 minutes, but I'll just show you the first 3 minutes to give you the idea.
Lampland and his wife are attending the 1937 meeting of the American Astronomical Society at Indiana University, the university from which Lampland graduated in 1902. Joined the staff of Lowell Observatory soon after graduation and remained there for the rest of his life. Hubble Nebula is found to the northeast of the Orion constellation in Monoxide.
Can people still hear me?
Yes, you're still good, John.
Okay, I think my computer's having trouble doing Zoom and showing this film. So perhaps I can come back to that. It's not boding very well for showing film. There's quite a lot of movies in this talk, so we'll have to hope that the other ones work better. They're a lot shorter than that. Anyway, if we could have seen some of the film, it would have shown some essential features of the variability in the nebula, which Lampland noted, which were that there's a fan-shaped reflection nebula above the star. The variability consists of dark areas that enter from the right, cross just above the star, and then tend to move up the left or eastern limb of the nebula. On occasion, one entire side of the nebula is obscured. The nebula shows a repeating stripy framework, which I'll show in a moment, which is like static, and the dark shadows move over that. And I think Lampland, initially people didn't really realize, weren't sure what these things were. Was it material moving? Because people didn't know how far away the nebula was. They couldn't see it. They couldn't tell how fast the space velocities of the darknesses were. But eventually they realized that if the nebula was at any distance at all, these things were moving very, very fast, and therefore likely to be shadows cast by something moving near the star. So now we come up to the modern day. This is just a sort of brief description of the sort of environment of the nebula. 2261 is associated with NGC 2264, which is a sort of open cluster or a young cluster of stars, which is currently forming. So there's lots of molecular material and reflection nebulosity associated with them. So this picture here, which I've stolen from Astronomy Picture of the Day a few months ago, shows NGC 2264 and various famous nebula like the Christmas Tree Nebula, Foxfur Nebula, I believe one of them's called. And the object that we're interested in is this tiny little blob bright blob down here. So it's really quite small. It's only one arc minute in size. But it is associated with this big area of star formation. This is a photograph, another photograph, of primitive technology taken at the Anglo-Australian Telescope by David Malin, who was rather good at that sort of thing, I think back in the 1970s or 80s. And he's treated it with a process called unsharp masking, which brings out the faint nebulosity. So you can see Armon, which is the star at the bottom here, a fan-shaped nebula, and faint nebulosity extending up to the north. Now, the static pattern, or the repeating pattern that Lampland mentioned, is these bands, stripes in here. And also there's sort of various sharp cutoffs where the brightness suddenly drops off in the nebula, sort of steps. So I've tried to I did a drawing 30 years ago now, trying to sort of show where I thought these bands were. You know, obviously this is fairly subjective, but it does sort of help you understand what I'm talking about. And then this is a deep photograph, again at the AAT, which shows the large scale structure of the nebula. Armon is down here at the apex of this bright blob. It turns into sort of tube looking structure, heads up towards this point. And these faint nebulosities up here are actually Herbig-Haro objects, HH39. And Herbig-Haro objects are where very fast moving gas, normally from a young star, impacts the interstellar medium, and you get shocked heated gas, and that gas emits line radiation, which we can see. So what we think is happening is there are quite a few observations of fast gas inside this nebula down here. What we think is happening is that Armon is a young star with an accretion disk around it. They tend to produce high velocity gas towards the star's poles in a jet, and that jet is going up the core of the nebula, the axis of the nebula, and is hitting the interstellar medium at this point. Now this should be symmetric. This is a symmetric process. You know, there's a disk in here somewhere, which has a top side, which we're seeing, and a bottom side, presumably with a jet coming out of the south, which we're not really seeing, except in this very deep photograph. So you can see some faint nebulosity here, and here what could be, if you use your imagination a bit, like a searchlight of light coming down here, illuminating possibly a very thin shell, that sort of thin dark line. So I've already said this. What do we think it is? Well, I think it's been known for some time that Armon is a young star. It shows all the characteristics of a star that's in the process of late stages of formation. Distance is estimated by its association with NGC 2264. There are stars in 2264 which the Gaia satellite can measure the parallax of directly. So that comes out at 719 parsecs. People have measured the radiation coming from infrared radiation coming from Armon, and we reckon we can estimate the total amount of radiation coming out of it. And it's actually quite powerful. It's 1,000 solar luminosities, 1,000 times more powerful than the sun, which stellar theory indicates that the star forming is about 10 times the mass of the sun. It's associated with, been known since the 1960s, it's associated with strong infrared emission, which implies it has a circumstellar disk. And when I first looked at it in 1989, after my sort of lazy afternoon in the UCL library, tried to estimate what might be casting the shadows that cause the dark patches to cross the nebula. And it turned out that if they were moving at some sort of orbital velocity, then they would be moving in an orbit about 0.3 astronomical units from the star. So this was the sort of 1989 model, which I've tried to draw. You have the star forming in here, surrounded by an accretion disk, where a disk is coming from, material is coming from the molecular cloud that the star formed from in through the accretion disk and onto the star. Some process near the middle of the accretion disk and the star is generating a very fast jet of wind, which is going out towards the poles to the north and south. The thing that's unusual about Armon and Hubble's Variable Nebula is there is this hollow shell to the north, certainly of the star, which is illuminated by starlight and is acting as a giant screen onto which shadows of things rising up from the accretion disk are falling. Counter nebula should be there, but is not really visible. So why is it important? I'll put this in the middle of the talk because it hasn't really changed. The important thing is that these small details of the accretion disk or something near the things happening near the star are being thrown onto this gigantic screen. So what we have here is a very common object. There are lots of stars forming, but what's uncommon is that the screen is nearby, which is showing us stuff that we can't see by any other means. So things happen. This object is so far away from us that 0.3 astronomical units is far too small a distance to actually be resolved by telescope on the ground, even if we could see it through the obscuration. So this is really a sort of, I would say, unique object. I think all reflection nebulae around the young stars are potentially this interesting, but this is the star. This is the, I was going to say the star, the star of the stars, because it's so well presented to us. So new observations. I'm afraid there are going to be quite a lot of movies, which I hope work. We'll see. These were all taken by robotic telescopes. Started off using the Liverpool Telescope, which is on La Palma. It's a 2-meter mirror telescope and produces very nice, sharp images. I don't think this photograph, the foreshortening, sort of exaggerates the size of the telescope, so it's not quite that big, but it's still a pretty impressive piece of kit. The great body of what I've done is using the Las Cumbres Observatory, which has I don't know, 10 or 15 telescopes dotted around the world. And it's really great. I mean, they're all robotic. You just schedule observations, and the observations get done on one of the telescopes when time is available. And it's great because, you know, it's very unusual for weather to not rule out. I think it's ever happened in my experience. So if it wasn't for the fact that loads of other people were trying to use the same telescopes, you know, I would have a great sequence of images. But as it is, it's still very good. And this is one of I tend to use the 1-meter telescopes, which are shown here. So I think this is the one in Texas, which are quite nice telescopes. They're not quite don't give images that are quite as sharp as the Liverpool Telescope, but they're getting better. And I should give credit to a chap called Alex Schultz at St Andrews University, who gave me the time on the Cumbres telescope network, and SUPER, the Scottish University's Physics Association, something, who I think clubbed together to sort of buy 1 or 2 telescopes for the Les Cumbres Observatory, and consequently have a big share of their time. So I'm grateful to Alex for letting me have some of that. Right, so this is the data. This is the straight data from R and I band filters. The red number is the modified Julian day of the observation. And I've made an effort to sort of make time flow evenly so that things move at their real speed. So this sequence started in early spring 2017. And I think I was lucky. I just caught the nebula in a period, at the end of a period of quite sort of high activity. And it's been getting quieter and quieter ever since. So I'll just let it finish and I'll go back to the interesting bit. Right. So at the start here, you can see these are what I would call a major shadow event. So you see things appearing at the to the right of the star, moving across above the star, and then moving up the left side. As Lampland saw. So I think the nebula is still doing the same thing as it did in his day. So that's the basic data. I've been taking data. I've been trying to take data daily, and depending on how busy the telescope network is, I get them daily or sometimes like once every 3 or 4 days. But it's good enough to actually sort of track the shadows quite well. Now this is an old slide from a previous talk actually. I added this one because at about the time I was starting to do my observations of the variable nebula with the Liverpool Telescope, an amateur astronomer in Arizona called Tom Palakis put up his movie of variability he'd observed in winter 2015, which is the video shown on the left here. And I think he's got a 15-inch telescope in a fairly suburban part of Tempe, which I think is a suburb of Phoenix in Arizona. But he does get lots of really interesting sort of video results, which he posts on Facebook and other places. So anyway, I think you can see that he's seeing the same sorts of things. He's seeing things move across from right to left and then go up the left side of the nebula. Now I've tried once a week. I try and get a complete set of sort of different color filters of the nebula. So this is the nebula from the Sloan Digital Sky Survey in its various colors, and you can see that it looks like the middle of the nebula is blue, and outside the nebula is more red. It looks like a sort of blue liquid in a sort of red sort of glass cup or something in some situations. So I've made tried to make a color film of the nebula variations. Things go a lot faster because there's only one set of data per week at most. And there's obviously quite a lot of fringing and stuff going on in some of the filters. But you can see the major shadow event, I hadn't really got my sort of observing mojo going properly, so it's not terribly well sampled in terms of time. So there are big gaps, but you can see it going up here, and it affects, the shadows affect all the colors, but they seem to affect blue more than the red. And I think that could be because the red is coming from a thicker sort of reflection. I think the blue gets absorbed quite quickly near the sort of inner surface of the cavity, if you like, above the star, and the red penetrates more. So the shadows are actually sharper in blue than they are in red. So that could be why the shadow appears to sort of go, well, affect the blue more than the red. I won't say more than that. Okay. So this is just a note to remind me what to say. It looks like a red glass filled with blue liquid, really. In the red, the nebula is much more spiky. You have sort of rays coming up from the star, going out into the interstellar medium. In blue, it's much smoother, especially up the eastern limb. It's a very smooth sort of surface it seems to sort of trace out. Okay. What to do with this data? I find it quite hard to. I found it quite hard to sort of tell what was shadow and what was actually just static pattern in the nebula. So I was trying to sort of think of ways to improve, to try and distill the shadow pattern itself from the static pattern. So the first way I tried to do that was to take all the observations and try and develop a sort of median image of the static nebula by taking a median value, literally a median value of all the observations I had, and then dividing that into each individual frame measurement of the nebula, so that ideally you would just get the shadow pattern left. So this is that. This is the resultant video. And it does indeed show the, I think it does show the shadows much more clearly, and shows how complicated they are, really. I was hoping this was going to be a sort of simple thing to understand, but no such luck. So I'll just let it run to the finish, and then I'll go back over the earlier stages again. Okay, so this is the major shadow event, which again is not terribly well sampled, I'm afraid. Then that calms down a little bit, and then we get another sort of secondary event here, where you can see smaller things lower, nearer the star, moving across the nebula. And then it gets really quiet. But when it gets quiet, you can actually see these faint ripples, well, I call them ripples anyway, like sort of arcs of light moving up away from the concentric away from the star. And I think they're really potentially quite interesting. I wasn't entirely satisfied with that method of getting rid of the static pattern, because when I looked at it in more detail, it seemed that there was really no such thing as a static nebula. All over the nebula, the light level was changing all the time, even though it's not immediately obvious to the eye. So I thought I would try and be a bit more clever and use this thing called a Mexican hat or Wicker wavelet filter, pass it over the time sequence of data. So what this does basically is this plot here, this is your time sequence So for each pixel in my data cube of through time, you would see some sort of varying pattern of brightness. If you convolve it with this this waveform, then it takes out slowly varying structures like the static pattern and leaves in the high frequency structures, which are the sort of hopefully the variability that we're interested in. And what in fact happened was it took out the major shadow event, but left other things which were more subtle than that, which weren't really visible in the my first effort. So it was worthwhile. So sorry, there's quite a few videos. So it's a bit confused near the start because the time sampling isn't very good. But now, there's a confused period there. You can see the ripples much more clearly, and at times you can see sort of spokes or filaments, curved filaments moving around north of the star. They'll go away and they'll come back again shortly. Yeah, sorry, these are the spokes I'm talking about. You can see them maybe 10 or 15 arc seconds above the star. And they're sort of curved scimitar-shaped things moving around from right to left. And back nearer the major shadow event, you can see bigger versions of them sort of moving around the star in the same direction. Later on, you can see the ripples from the star much more clearly in this way of in this analysis. So the things I'm talking about are these curves, which never cross each other and always the same shape, and move away from the star steadily, just like ripples. So, how to analyze these ripples? I think they show that they confirm really that the reflection nebula is a single reflecting surface. It's acting like a giant cinema screen. In that, taken this diagram from a paper by Ortiz et al. But if you think about it, a light shell from the star, a light shell moving away from the star, arriving at our telescope on Earth, it's actually like a telescope in reverse, in that if the Earth and this arm on the star are at the foci of an ellipse, a giant extended ellipse, then one of the few things I remember about ellipses is that the distance from the focus to the curve of the ellipse to the other focus stays constant. So that's basically telling you where on the reflecting surface you would see light coming from at any given time. So this is their diagram of that ellipse, or in fact a parabola, which is an ellipse with focus at infinity. So at time one, you have this, what's my pointer? At time one, you have a parabola on a certain surface, and which shows that light must be hitting that surface to be seen by you. At time two, the surface is moved out slightly, and very subsequent times it moves out further and further. Now, I think this shows that if on the left, in the left-hand diagram, there's a relatively thin surface, the grey circle. That would show you what we see as a ripple moving away from the star. if the matter was distributed in a way more in the right-hand diagram, like in just a clump or something solid like these squares, then you would see something much more fuzzy and complicated. So I think the fact that we see ripples does indicate that it's a single fairly thin reflecting surface. And I can use that together with an assumed distance of 719 parsecs to generate a 3D model of what the shape of the surface must be, which is this, which I always have trouble moving around. But to try and explain this diagram, this diamond down here is arm-on. This line is coming towards the Earth. This surface is what I think the 3D surface shape is of the reflection nebula. So this is us looking at. This is our view of the nebula. So the star's down here. This black line here is the eastern limb of the reflection nebula. And I think if I can never control this properly. But if I swivel it around, you can see that the limb of the nebula is a similar shape. Similar, I'll say no more than that, to the 3D shape of the nebula estimated by using the ripples. Right, so I'll try and get rid of that. So if you know the 3D shape of the reflecting surface, you can try and remove the time delay associated with the shadow, analysing the shadows. You'll notice that you will have noticed, I think, that all the shadows stretching up from arm-on were curved. That's because it takes light quite a long time to move from arm-on up the nebula. It's a bit like sort of waving a sort of water hose above your head. You know, if you move it quickly, then the water drops will show a sort of curved, appear to follow a curved path, and I think that's what we're seeing. But if you know the shape of the reflecting surface in the nebula, then you can take out that time delay. So that's what I tried to do here. This probably takes quite a few times to looking at it to understand what's going on. But you should see lots of sort of vertical bands or spokes moving around the star from time to time, not all the time. Like there. And the whole nebula is getting brighter and darker as to get in synchrony with itself because the time delay has been taken out. So it's showing the variability of the star at the center of the whole thing. I'm getting a bit low on time, so I better sort of. I mean, that's the most the variability stuff is the most interesting part of this object, I think. But there are plenty of other observations which have been made. For example, this is data from the Herschel satellite, which looked in the far infrared all over the sky, but did look at arm-on and 2261. And I've recovered this from a tool called ESA Sky, which can be found at this web address, which I can't really recommend highly enough. It's not just the fact that all of ESA's spaceborne data is there for anyone to find, but it also has a really good link to literature sources for any object that you can think of. So my story about John Edward Mellish, which I started off with, I found through ESA Sky, which I would never have found otherwise. Anyway, this is what the object looked like at 70 microns. So at this long wavelength, you're looking at thermal emission from dust. So the things that you're seeing are where material is and how hot it is, or how warm it is. It's not really hot. So you can see the star itself down here in a big blob of material. This looks like a limb-brightened edge of a cavity, as it does in the optical. This is a sort of blob, which again is sort of something we see in the optical. So I think this is showing that there's warm stuff that can see the star, and there's quite a lot of it. This is at a longer wavelength, which is more, is looking at a cooler temperature, if you like. So you can see much more material around the star. And particularly interesting here, I think, is that there's a cavity below the star to the south. There just doesn't seem to be very much material there, apart from this faint blob, which I think pretty much matches where you see a very faint reflection nebula in the south of Armon in the optical. But basically, I would contend that the wind from the star, the jet from the star, has blown away any material in this area down here. And there is basically the main reason we see nothing to the south is that there is nothing there for the light to reflect off. Other people have looked at the carbon monoxide emission from the area, which also shows the cold molecular material there, but also shows its velocity. So you can see this is showing blue shifted gas here. So you can see that there's blue shifted gas north of the star, red shifted south of the star. And these other things are just different velocity channels, which are showing basically the same thing. This is a cut through the star, so Armon is at 0, I think. And you can see the rest velocity of the cloud must be this line here, about 9 kilometers a second. You can see that there's hardly any emission associated with the gas north of the star, which isn't moving towards us. And similarly, south of the star, there's nothing that isn't moving away from us. So I think that means that there's basically just one side to the shell. North of the star, it's on this side of the jet going north of Armon. South of the star, it's moving away from us. It's on the far side, and there's not very much of it. There's very much less emission down here than there is up here. Hubble Space Telescope. It was observed once in 1995. This is an APOD picture produced by Judy Schmidt. It's a very nice, clean reduction. This is my reduction, which isn't nearly as good, but shows how red the nebula is, or how red the nebula is at the edges. You can see a faint trace of the blue nebula here, and you can see a small nebula down here, which is actually quite blue compared to the red nebula further north. So I think this is really quite interesting. There's a big nebula to the north, and below that there's what I've called the small nebula, which is directly associated with Armon, which is so small that we don't normally sort of easily differentiate it in optical photos. This is something I've reduced from the HST as well, which is from the HST Planetary camera, which is the highest resolution imagery you can get from the HST. This is the small nebula, and I think it's really quite an interesting object, really quite an interesting image. This is Armon, slightly sort of washed out in the red here. This is a companion star called Armon B, which is deeply embedded in red. This whole, notice how small this is. This is 2 arcseconds, so it's really pretty tiny. There looks to be a sort of cone shape, maybe a hollow cone with an opening in it at the bottom here. We can see a blue interior. You can see something that looks like it's inside the cone being illuminated by the star, a sort of sausage shape casting shadows. And I think here you can actually see a shadow cast on the cone by this bright spot of the sausage-shaped bit down below near the star. This is from the VLT, an infrared camera called NACO, which uses adaptive optics to take out the shimmering of the Earth's atmosphere. So this is actually an incredibly sharp image. It's the full resolution of an 8-meter telescope. And I've plotted them on the same scale. If I flip between them, you can see that this blob here is around arm1, has become symmetric around arm1. So this is K is at 2 microns, so it's a much longer wavelength. So we're seeing much less effects of obscuration. So we can see the top part of the South Nebula at least. This curve up here matches the curve on the edge of this bowl in the HST image, exactly. So I think there's a huge gout of sort of optical radiation coming out to the northeast up here, which we're seeing at both wavelengths, optical and near infrared. So what does this say? I'm sort of running out. I've run out of time, but I'm sort of getting to the end here. What does this do for the model that I had in 1989? Basically, there's a single reflecting surface. The front of the cone only is present. The southern lobe is obscured near arm1, but is absent because of a lack of reflecting material further out. There is a small nebula and a big nebula, which are sort of associated with each other. And there, I think, it's possible to conjecture that there are links between the two. So this eastern ray that we can see developing in the small nebula, I think produces, can be seen all the way up the eastern limb of the nebula in larger scale pictures. And if that's true, you can follow the major shadow event up the eastern limb for 180 arc seconds. It takes about 670 days to do that, to cover that distance, which equates to a speed just over the speed of light, if we assume the distance of 719 parsecs. So I think it's quite consistent with arm1 actually being, really is part of the NGC 2264 cloud. And if this is really conjecture, but some of the static structure in the nebula, such as the rim, there's a rim across the middle, the midriff of the nebula here, could actually be caused by the edge of this cavity. Come on. In the small nebula. So I think it's possible that we're beginning to sort of see connections between small and large, for sure. I think I'll leave that out because I'm sort of, it's quite hard to explain. What I'm trying to do here is trying to work out what the, if the thing moving near the star, which is casting those spooky shadows, is at a certain, has a certain axis, what might that axis be? And I've tried to do some sort of geometrical modeling, and it indicates that the position angle of the thing that's spinning is about 15 degrees from north, which is slightly different to that of Herbig-Haro 39, which is always thought to be the axis of the nebula. So it seems like things aren't quite may not be quite lined up as we would expect in the center of the target, center of the source. Major shadow events, I mean, they're the reason that I sort of first got interested in this, but unfortunately, the data I've got doesn't really cover it, any of them very well. Certainly they're opaque and massive, and they tend to much bigger solid angle at the star. Currently, I think they might be some sort of thing ejected from the disk in the same manner as a coronal mass ejection is ejected from the sun by magnetic forces, but that's really just guesswork. So conclusions, at last. The most important thing is that arm1 is an ordinary star in an extraordinary position, projecting its sort of private affairs onto a giant screen. to understand what's going on, we need to try and understand the screen shape, and I think there are signs that we're starting to do that. It offers a unique view into the central few astronomical units of a star-forming system. But even after 100 years, studies are still at a very early stage. So to show, this is the very last slide. This is Liverpool Telescope data from the archive, so it's nothing to do with me. I think most of it was taken by the schools project, always in H-alpha over about the last 20 years. And all I've done here is put the images in order and make a film of them. They're not, so that time isn't flowing smoothly in this case. But if I play it, it shows much more of the sort of full realm of what can happen in the nebula, which one might hope to see if we carry on looking at it. So, particular interest is about this time, you get sort of straight shadows appearing, coming up on the nebula. Now, straight shadows means things that aren't moving in azimuth. So you don't get this like sort of water come from a hose effect of light bending because of its finite speed. So the things casting these shadows aren't in orbit. So what are they? There's something that's popped up or is falling into the plane of the system. So something different than I've seen in my closer observations. And there are much bigger shadow events to see, like this one, where most of the nebula goes dark. So my plan is to carry on looking as long as Alex Schultz will let me have telescope time, and just hope that something, that the nebula continues to do its thing and we catch something much larger. That's it. Sorry, I went over time.
That's okay, John. That's no problem at all. Oh, thanks very much for that, John. That was a really fascinating insight into Hubble's variable nebula. On it being confused with comets, I had a report of it as a comet a couple of in the last couple of months. So people still confuse it with comets. If anyone wants to ask any questions, if they can either use the Q&A on Zoom or the chat on YouTube. There's a couple of questions on Zoom.
Did you want me to handle them, Callum, or you?
It's okay. I'll look at them. Sorry, the first one was just a general introduction from one of the gentlemen who's dialing in from Italy. Welcome along this afternoon. Hope you find the afternoon's talks interesting. And second one from Daryl. Is there any interaction between ARM1 and ARM1B?
No, I don't. Well, yeah, I don't know. I don't think so. I mean, at one stage, in this image here, some of the more you look at these things, the more patterns you see, or at least I do, which is a bad sign, really. It's funny how the Canals of Mars were mentioned earlier on, but there are some lines here which go across sort of in that direction, which seem to point back towards ARM1B. And at one stage, I was wondering if this red light over here was actually coming from ARM1B. I don't think it is, because ARM1B, people have measured the amount of radiation coming from ARM1B, and they think it's a much smaller star, and therefore producing much less energy. So I'm sure they are interacting, but ARM1 is very much the dominant partner.
Question from Kevin: has there been any spectroscopic studies?
Yeah, I didn't have time to talk about those. Glad to know. Yeah, I mean, it's quite notable in spectroscopic studies as well. George Herbig of Herbig Hero fame and a collaborator, I think back in the 1980s, people before that were as well, did long slit spectroscopy of the fan above Armon, and they put a spectroscope slit through Armon and up the nebula, and they found that the hydrogen lines showed strong absorption above the nebula, which got broader the further up the nebula you went. So they interpreted this as being showing absorption by the wind from the star, and as you went further up the nebula, you got a more and more sort of from the top view of the star. We're looking down into the wind from a higher latitude, and we're seeing a higher velocity component. So at the top of the nebula, they were finding lines that were maybe, I think, 200 or 300 kilometers per second wide. Lower down the nebula, they were much narrower, and they fitted a sort of relation to them, and that was their interpretation. But I think it shows that's the great value of this. You can tell an awful lot more with spectroscopy, and if people believe that there is a simple screen, a very sort of smooth screen, it seems, above the star, then you effectively get a view into the star from a variety of angles, and spectroscopy will be able to tell you what's happening at different angles in the system. And indeed, if you see a shadow moving across the nebula, if you can get some absorption lines associated with that shadow, and you can tell what the radial velocity of the thing is that's casting the shadow, which would be great, and something about the physical conditions. So yes, it has been done. It's started, and it looks very interesting, but it's only just been started, really.
There's a question from one of our YouTube viewers, Andre, asking what tools you use for measuring the brightness of extended objects. So I guess some sort of integrated magnitudes, or do you not really measure the absolute, or sorry, the apparent magnitudes in that way?
Well, to do well, I mean, the only sort of calibration I do for the movies is on just using the stars in the field. So I use source extractor and SWARP, and just basically everything in astromatic.net software collection to actually do the calibration between different images. I haven't really been doing very much sort of absolute calibration of the data, so that's about as far as I've gone.
Okay. Steve asks, will the variability of the nebula eventually disappear?
Yeah, well, it might already have done that. It could be really irritating since we just started looking at it. But no, I don't think that was a joke. But yes, it will stop. Because the star formation process will calm down. But that might take tens of thousands, hundreds of thousands of years. It's a mystery to me why and how the screen has formed in the way it has. Why it seems to be so smooth and unbroken. But as long as it's there, then we should be able to have our various viewpoints into the star as it forms. And as long as the star as it forms continues to throw up lumps and bumps, as long as it continues to have an accretion disk, then we should be seeing things.
And one from John Morell. Do the long period variables that are embedded in the nebula or perhaps are behind it have any influence on the variability?
No, I don't think so. I think all the illumination is coming from Arm1, so that's the only thing that we're seeing.
Question from Davido, who I think is our visitor from Italy. we'd like to ask what is the time measure reported in the frames, and what is the I and R suffixes meaning?
Oh, right. Okay. The time measure is the modified Julian day at which the frame was taken, and the I and R are the names of the filters used for the image. So I think I started off with R, and then for some reason I thought that the I images looked sharper from the less cumbrous telescopes, so I switched to I, which is probably a mistake because it means I thought I gave up the sort of uniformity of my data set. But since then, since that change, I've stuck with it. So yeah, they're the Sloan Digital Sky Survey I and R filters.
There are a few more questions. I think maybe if as we're getting short on time, well, not really short on time, but time is pressing on. Maybe we could forward those on to you, John, and we could get you to respond on those after the meeting, and we'll get back to the people that have asked those questions, if that's okay with everyone. Sorry about that. We should press on, I think, with the next talk. But I'd just like to thank John very much for his talk today. It was really fascinating and interesting, and I know a lot of our variable nebula team of observers will be really fascinated to have heard that explanation of what's behind Hubble's variable nebula, and maybe use that as some insights into some of the other variable nebula that we observe, and might inspire a few more members to have a look at the small number of variable nebula that we have up in the sky. So thanks again, John. We not really able to give rounds of applause, unfortunately, through this means, but I'll give you a round of applause. So thanks very much, and we'll thanks for joining us today, and take care. So if I can move on to our next speaker, I'm very pleased to welcome Peter Goodhue. Peter is a BAA member, a regular observer of planetary nebulae, and we came up with this slightly enigmatic title, Discovering Planetary Nebulae, and hopefully over the next 40 minutes or so, Peter will be able to explain a bit more about what he does. Over to Peter. Are you on mute or anything, Peter?
No, I'm here now. We seem to have you rather than me on the main screen.
I think you're on the main screen now.
Oh, okay, fine. It's,
when
right.
you speak, it promotes you to be the kind of the main person who shows.
Right. Okay.
And also, once you start sharing a presentation, that will switch over to the main one.
Right. Okay. I'll start sharing then. I think that's the best thing to do. Right. Can you see that? My first screen?
Yep,
my presentation?
Good. Yep, that looks good.
Excellent. Okay, good. Right. Thanks, Callum. And yes, so this sort of slightly enigmatic title. I've loved imaging planetary nebulae for a few years now. I find them incredibly attractive, beautiful, and interesting. I say some of the most beautiful objects that you can image. And about just over a year ago, I think 15 months ago, I unexpectedly got drawn into getting involved in the process of discovering planetary nebulae. And the last year has been a year of surprises for me. There's an awful lot of things that I didn't know, that I didn't expect to find out. And I'd like to share with you what's happened in the last year. And I mean, I have played a supporting role in the discovery of planetary nebulae, primarily through the imaging that I do. So if we, I mean, let's just talk about some of the things that I've learned and have been shocked or surprised with during the last year, to sort of misquote a certain actor. Not a lot of people know this, and I certainly didn't. First of all, I was surprised that there were no amateur discoveries of planetary nebulae throughout the entire 20th century. And it was exclusively the domain of professional astronomers. However, in contrast to that, now amateurs are making new discoveries every week. And that's become possible really since the advent or the availability of digital sky surveys, and through the accessibility of those through the internet. Another interesting or surprising fact is that many planetary nebulae have never been photographed. They may have been identified, or candidates at least, they may have been identified on a sky survey plate, but nobody's ever got around to photographing them. And part of the reason for that is that many, especially the newer ones, they are very faint, and we'll go into why that is. And so you need very long integration times, typically up to 50 hours of imaging. In fact, I think in one case, I exceeded 70 hours in order to produce a usable image. So that's discouraged people from photographing them. And the other thing which I also find astonishing is that most of the new discoveries remain unconfirmed. We don't know for sure if they are planetary nebulae. Either they've not been photographed, or if they've been photographed, we've not yet got a spectrum, which is key to confirming them. And part of and the other thing, which is also a bit surprising, is that actually verifying that something is planetary nebula is incredibly difficult and very complicated. And so, I mean, all of those factors really, I just thought that, we knew everything, we'd seen everything, we discovered everything. And I didn't think there was a role for amateurs in this. And I didn't realize that so much could be discovered and is being discovered every week. So how did I get into this? Well, I live in Chiswick in West London. I got my first telescope 8 years ago, I think. After several years of frustration, it dawned on me that, to try and do imaging of faint objects with English weather, with London light pollution, and being directly under the approach path to Heathrow Airport was pretty insane. And so I made the decision that I should relocate. And so I moved my telescope to Spain. And here you can see it is in Spain. I'll play a short clip so you can see the telescope parking itself. And what I've got here is two 6-inch refractors. It's fully robotic, fully automated. This is about 150 kilometers north of Seville. You'll notice the sky is blue there and there's no cloud. There's a reason for that. Technically, this is actually a desert area. It gets about 280 clear nights per year, which I think pretty much matches the 280 cloudy nights a year that I was getting here in London. And because I've got the two twin scopes, and if you look, take, for example, this time of the year, there's about 12 hours of darkness. So I can achieve a combined 24 hours of imaging per night, which is more than I was achieving on average in a whole month back here in London. Another bonus, which I hadn't fully appreciated, is that being so much further south, I get better access to the southern hemisphere, and I can easily image things which are sort of declination -20. So this gave me a deep imaging capability, and that meant I could go after really, really faint things and do long exposures and image things perhaps with more integration time and more depth than had been done before. And because I was doing lots of planetary nebulae images and publishing them, I started to attract some attention. And I was contacted by a gentleman called Sakib Rasool, who I think lives up in Lancashire. Although he's an amateur, he's a world authority on planetary nebula. And he started sending me almost daily imaging requests for me to image something that either had never been imaged before, or hadn't been imaged in great detail, or hadn't been imaged in color, and so on. So I ended up getting more and more, spending almost all of my time imaging planetary nebulae. Many of them I'd never heard of before, and many of them had never been imaged before. And I have to say that to actually produce an image of something and see it and be the first person to see that, well, I got quite a buzz from that, because I never imagined that I'd end up being able to do that. How did all this start? Well, who was the first amateur? Well, you're all familiar, or mostly familiar with Charles Messier. He was interested in comets. He wasn't interested in planetary nebulae at all. He produced his catalogue of 110 objects which weren't comets and were to be ignored. And 4 of those happened to be planetary. We now know are planetary nebulae. He didn't describe them as such. It was only really when William Herschel produced his catalogues that the first documented reference to things being planetary nebulae was found. And so we suspect that William came up with the idea. He described them as planetary nebulae, even though they have no connection to planets, because they had a sort of an appearance which was sort of a cross between the appearance of a planet and the appearance of a nebula. They were fairly bright, but they didn't have the sharp edges that you would associate with a planet. We now, out of his 2,500 objects, 70, 80 classified in his sort of subcategories or subcatalogues as planetary nebulae. But again, he didn't know what a planetary nebula was in the true sense that we now understand them from an astrophysical perspective. And we know now that many of the things that he described as planetary nebulae were not actually planetary nebulae at all. Some, for example, were distant galaxies which looked quite similar. So his classification was really just based on the morphology, on the physical appearance, without really knowing what a planetary nebula was. And it wasn't until 1864 when a guy called William Huggins started doing a lot of spectroscopy. And he did the first spectrum of a planetary nebula, NGC 6543. And looking at that, it was quite obvious that it was very, very different to stars and star clusters and what we now know to be galaxies. All of those would have a continuous spectrum, and we had very distinctive emission line spectrum for the planetary nebula. So again, first clue that astrophysically, these were very, very different objects. But it wasn't really until the beginning of the 20th century that we started to get a clearer understanding of what these things are. Now, I think most of the people in the audience will be familiar with that, but to ensure that everybody has a common level of understanding, I'll give an idiot's guide or summary to what they are. So they tend to be small to intermediate mass stars, so between 0.6 or 8 times the mass of the sun. And when stars get to the end of their life, stars are normally in balance between gravitational pressures and the pressure, the external outward pressure that comes from the nuclear reaction that goes on within them. As they run out of fuel, the nuclear pressure declines, and they go through gravitational collapse. That collapse then results in an outer shell being ejected, and that as that shell is ejected, it exposes an extremely hot core. That core emits intense ultraviolet radiation. Now that radiation in turn ionizes the outer shell and makes it glow, and that's the thing that we see, and that's what gives those emission lines. They tend to be fairly short-lived astronomically, about 30,000 years, and they start off extremely small as the shell leaves the star, and extremely bright because they're quite compact, and also the radiation is very intense. As they get larger and fainter as they evolve, as the shell moves out from the core, and so it dissipates, it gets more diffuse, but also as the distance increases, it gets less intensity from that central core, it gets less UV radiation. So they get fainter and fainter until eventually they disappear into the interstellar medium and just become another contribution to stardust. And this is key in terms of both discovering them and also imaging them, because if they're very, very small and bright, then you need a very long focal length telescope in order to be able to see them, but they're extremely bright, so it's quite easy. If they are large and faint, you don't need so much a long focal length telescope because the object is much, much bigger, but you need extremely long exposures. And as they get more and more evolved, more and more mature, they get fainter, then you end up with imaging times which get longer and longer and longer. And I think this is why the earliest ones that were discovered were all pretty bright, because they were easy to see just through a telescope. And I think it also explains why in the 20th century, it was only professional astronomers with large telescopes that could actually discover them. In total, over 3,000 have been discovered now, but there's estimates that there could be about 50,000 throughout the galaxy. Some will be too distant, and some will be obscured by dust and gas that makes them not visible. Larger stars than 8 solar masses are likely to end their life in a supernova because they've got greater scale in order to trigger that. And it wasn't really until the end or the beginning of this century that it was possible for amateurs to start getting involved in discovering. What happened was that digital sky surveys became accessible and loaded up and available on the internet. And in June 2003, a group known as the Deep Sky Hunters, it's an international collaboration of amateurs from around the world, got together through a Yahoo group and started collaborating on searching the skies for things that hadn't been discovered before. The group was assisted by a professional astronomer, a guy called George Jacoby. George is an interesting chap in that he previously in his career had been involved in designing the main rockets for the space shuttle. But once he sort of finished with that, he decided to move into more of an astronomical career and ended up running one of the big telescopes at Kitt Peak National Observatory in Arizona. And this was fortuitous because George was able to get time on the 3.5 meter telescope there, so that if the group found something, he could get the telescope looking at it and take a good look at what they'd found. And because these sky surveys, the best thing you're likely to see is a faint smudge. And it's hard to tell from a faint smudge what's really there without you getting a beefy telescope to take a closer look at it. So the group were not interested in planetary nebulae at all. They were interested in star clusters, and that was their focus. However, after a while, a guy called Patrick, who was one of the group, was looking for star clusters, and in 2003, he accidentally came across a planetary nebula. It's the one you can see on the left-hand side of the screen there. He was searching for open star clusters at the time. And Adam Block, who had, I think, graduated from college a couple of years earlier, was working at Kitt Peak, and so he took that image of the first discovery by an amateur since 1894. So that's quite a historic thing. But Downer carried on looking for star clusters, and then a couple of years later, he accidentally came across another planetary nebula, the one in the middle, PA5. And at that point, he thought, well, if I keep stumbling across these, maybe I should start deliberately looking for them. And so he did, and 6 days later, he found another one, PA6, which George Jacoby also imaged using the 3.5 meter telescope. A point about nomenclature here: when a planetary nebula is discovered, the convention is that it's given the first 2 letters of the discoverer's name and then the sequence number within the catalogue of all of their discoveries. If more than one person is involved in the discovery, then the first 2 letters of their names are combined together. So, and you'll see that occurring a lot later on. But what astonishes me is that although the middle PA5, the one in the middle, that was an image taken just a few months ago, and that was actually a 27-hour exposure by an amateur, Boris, who's very well known in the community. PA1, the one on the left, has never been photographed since then, even though it was the first discovery in over a year. So, and likewise, PA6 has never been photographed in color. So I've got them both on my to-do list for this year, and as and when they become available, I'll be using my telescopes to get the first deep color images of those, so that we'll be able to see what they really look like. Now, since that, the Deep Sky Hunters collaboration has largely become less inactive. George Jacoby has retired, several of the participants have retired, but Dana here has continued to be very active, and I was surprised and honored when he contacted me in January of last year to see if I could help take photographs of some of his discoveries from years back. I was honored and delighted, and I think I spent most of my imaging time in the last 15 months working on discoveries that Dana has made. Now, following on from that, more recently, a bunch of French amateurs have taken the leading role in terms of a collaboration. Here's just a few of the names on the left of some of the key amateurs that are involved in this. And they are specifically focused on discovering planetary nebulae. They have made 968 discoveries in recent years. Of those, 108 are confirmed, 13 are considered to be likely to be planetary nebulae, 13 are possible, another 573 have we've got yet to figure out what they are or whether they're not, and I'll come on to some of the challenges there. And 225 have been included as not being, they might be supernova remnants or other things. But the group does more than just discovering. They, some members of the group do spectroscopy, and that's invaluable in determining whether something really is a planetary nebula. They maintain a very, very good online repository called planetarynebulae.net, which has become the sort of de facto standard for amateur discoveries. And they are also currently in the process of a project called 2Spot, where they're setting up a remotely controlled spectroscopy telescope in Chile. It's been delayed by the pandemic. They were hoping to have it up and running last year, but hopefully within a few months they'll be able to do that. And key reason for that is that most of the spectroscopy and most of the research has been done in the Northern Hemisphere, and there's a lot to be still examined and checked in the southern hemisphere. Okay, now one of the guys there, Xavier Strottner, teamed up with a German guy, Marcel Drexler, in August, I think it was August of 2019. And these two gentlemen have been collaborating on discovering planetary nebulae since then. Their first discovery was in October 2019, which is what, 16 months ago. And since then, they've made an astonishing 300 discoveries. 240 of those are deemed to be planetary nebulae discoveries, of which 33 have been confirmed now as such, and the others are still waiting to go through the confirmation process. Their first discovery, again, all their catalog is called the STDR catalog, so the first two letters of their surnames. And their first discovery was made looking at the IFAS Hydrogen Alpha Sky Survey, which was done using the Isaac Newton telescope. And so this was classified, given the nomenclature of STDR1. And so this was the original Sky Survey plate that they said, well, look, it looks like there's something there. Let's find out more about that. But they needed to get some deep imaging done of this. And I was very, very honored that Marcel contacted me to ask for help in December 2019. And I was honored and immediately said, yes, I'd be delighted to see what I could do. Now, since then, Marcel's built up a broader network of other images because he and Xavier have been finding so much. They need a team of people to try and keep up with them. But anyway, I went and shot that image, and this is the result. This took me 20 hours of imaging to produce, but what it clearly shows, which you don't see on the Sky Survey, is the blue there that indicates that there is both oxygen and hydrogen alpha, the hydrogen alpha being the red. So this really is a comforting sign that this may well be a planetary nebula. And also it's got a sort of a spherical circular morphology, which also reinforces that. And I have to say that for me, it was an amazing experience when this image appeared on my computer screen, and I was the first person in the world to actually see this. I got quite a kick from that. So anyway, that was then taken up by the French team, and they did spectroscopic analysis. It's probably difficult to see, but they positioned the spectroscope just here, and the spectroscope came up with this spectrum. This is the air glow, and here you can see the hydrogen alpha and oxygen emission lines very, very clearly and very, very strong. And as a result of that, this became confirmed as a planetary nebula. And recently, Rochus Hess, another of Marcel's friends, managed to use a 1 meter telescope and get 16 hours of imaging to show that that discovery in much more detail. And I think that's it's quite a remarkable first discovery for Marcel and Xavier. Since then, a lot has happened. I've been spending a lot of time helping them. They've had a lot of other people doing that. But also Diana has been sending me work to do as well. And one interesting thing is that there are things which we've been looking at for years without realizing that they're planetary nebulae. And here's one example. Sharpless 2215 has been classified as an H2 emission region since 1959. And in fact, the image on the left was taken, I think, only a few weeks ago, because it's still considered to just be a hydrogen emission nebula. But Dana had noticed that this star here was extremely hot. He'd been looking at star catalogs, and it had the temperature that you would expect to find at the heart of a planetary nebula. So he asked me to image this, and I did, and this is the result of me imaging it. This took 43 hours. But again, it clearly shows a significant blue-green core here, which shows that there is oxygen present and that it isn't just a hydrogen emission nebula here. And as a result of this, this is now confirmed as Planche Nebula PA167. You notice that at this point, when Diana thought this was a potential Planche Nebula, this was the 167th discovery he'd made, and I think his total list of discoveries now comes out at over 300. That's quite a significant set of achievements. So how does one go about discovering it? If you want to start discovering some for yourself, you could do it tomorrow, I'm sure, but it's not a trivial exercise. You have to start by looking at sky surveys for unregistered nebulosity. And all of the easy to find stuff has been found, so it gets fainter and fainter. You then have to check for other surveys for corroboration. Because most of the sky surveys, or the one that most people start with, is just hydrogen alpha. And there's lots of hydrogen alpha nebulosity around, but that doesn't mean that it's a planetary nebula. So you need to look elsewhere. Mid-infrared is a good place to look. And there was a space satellite called the WISE, which was up in around about 2010. It was decommissioned after a while, but it did a hydrogen alpha survey, an infrared survey rather, of the sky. And looking at that, you can often find, if you find something there that matches the nebulosity, then that increases the probability that you've got something there. And there are a lot of other sky surveys that you can look at to see is there something else that suggests that this is more than just hydrogen alpha emission. You can look for a hot central white dwarf, hot enough to create ultraviolet emission. That increases the probability. And then, like I've been doing, get deep narrowband imaging in hydrogen alpha and O3. And if that shows up, then that helps. You can look at the morphology to see if it looks like the sort of thing. And I mean, you can look at them and you can say, yes, it looks like a Planche Nebula, but there are lots of things that look like Planche Nebula that aren't, and we'll see some of those in a minute. And then finally, you get spectroscopic assessment, and then you submit it for evaluation. And that's normally done by a team in Hong Kong now who maintain a database called HASH. They categorize Planetary nebulae in four categories. First of all, it's a candidate. It's just, I mean, this is a simplification, but a candidate will have unregistered nebulosity. So there's something there. It's possible if there's a hot central star, then it's more likely to be considered possible. If there's O3 imaging that comes through from photography, then it will make it likely. And if you get spectroscopic confirmation, then it's likely to be true. Now, this is a gross simplification, but it gives a clue to the sort of parameters that go through. The actual final parameters are far more complex than that and beyond my comprehension. But let's look at some common morphologies. So obviously a very common one is spherical morphologies. Here's a couple of ones from the Abel catalogue that I've done. And on both you can see it's a sphere, and you can see there's a bright blue star in the middle there and a bright blue star in the middle of there. And these are both confirmed as planetary nebulae. Other morphologies you get, you get a lot of bipolar planetary nebulae. And so you'll get two lobes, and there'll be a bright star somewhere in the middle there, but it's not particularly visible on these. So these are two bipolars, but sometimes it may look spherical, but it may be bipolar. And here's a couple of examples. And the thing is, if you look at a bipolar planetary nebula end on, it will look like a sphere. But what you'll see is that you might get this dual ring effect, which if you look at this this chart here, you can see that if you're looking at it from along the axis, the two lobes are likely to overlap and it will look like a sphere. If you look at it slightly offset, they'll be slightly offset and then you'll get that. So images like these are more likely to be bipolar, even though they may appear to be spherical. And then a famous bright one, which is elliptical, is Messier 57. Now, problem with morphology, there is an awful lot of things that you can find which look like spherical or they're bipolar, but in fact, none of the things that on this chart turned out to be planetary nebulae, although it was considered they were likely candidates at one point. So the problem is, well, okay, to be or not to be, is it mimics like that? They are likely to be either H2 regions, they could be galaxies, they could be reflection nebulae, they could be supernova remnants, even cataclysmic binary star systems where a shell is being ejected by the binary companion. So indicators which help eliminate these mimics are a lack of O3 emission. Obviously a spectrum will show it up, you'll get a continuous spectrum. You'll also, if you get a lot of strong redshift, then you know that it's too far away to be a planetary nebula that we can observe. If you get sulfur-2 emissions, then it's unlikely to be a planetary nebula. That's again where the spectrum comes in as being key. And sometimes you can estimate the size, the distance, the mass, and that would discount them because it's just too big, too heavy, too large. And also, if the morphology doesn't look right, then that may help. Here's one that was considered to be a planetary nebula, and I imaged it, and then it got declassified, and it's now actually downgraded to just ionized interstellar medium, even though for a while it looked very much like it was a planetary nebula. Okay, so what I'd like to do now is show you some of the discoveries that my friends Marcel and Xavier have made. Marcel has kindly put together a 3-4 minute video clip of discoveries, some of the more attractive discoveries they've made in the last 15 months. I think these are stunning, and I hope you do so too. So, and they start off with a map of the galaxy showing you all of the discoveries that they've made in the last 15 months. So here goes. Well, hopefully you'll agree that that's pretty impressive selection of things to have discovered in just 15 months. So if we look at the future, clearly there are many, many more discoveries in the pipeline. I think one of the things that I find frustrating is that we cannot announce them until they've been registered. A lot of effort goes in, sometimes hundreds of hours to make a discovery. And so people want to be sure that they get it registered under their name before anybody else can. And so I've got quite a lot of hours of imaging on my hard disk, which I can't share with anybody until we get to the point where it gets it gets registered and we can go public. There are a lot more images currently being done. My telescopes tonight will be are already programmed to go 3 different objects, which are either undiscovered or new discoveries that aren't announced, or potential discoveries of things which are already there, but we're not sure what they are until we get more deep imaging. And I have no doubt that Marcel and Xavier and Darnat will keep me busy all through this year. So that really concludes the talk. I'd like to say a particular thank you to Darnat, to Sakib, and to Marcel, who've all helped me put this presentation together. And now I'm happy to open up for any questions.
Well, thanks very much, Peter. That's really exciting to see that there are still things that amateurs can discover in the deep sky field of things. It seems to be an underappreciated field. Quite a few questions coming up, so I'll just run through those. First one from Simon asks, could we be very close to a very large and very dim yet to be discovered planetary nebula?
Yeah, I have no doubt we could. And there are some fairly close and bright planetary nebulae, like the Helix Nebula. The closer they are, obviously, the easier it is to see them, and the larger they will be in terms of angular size. So absolutely, and I think the very large, if it's close by and it's not discovered, it's going to be pretty damn faint. But that doesn't mean it can't be found. And some of the ones we've just seen are not that distant. Otherwise, they'd just be tiny dots. So absolutely. And
following on similarly, what is the nearest planetary nebula to Earth?
Oh, I don't know the answer to that. I'm tempted to say the Helix, but I'm guessing at that. Given its size and its brightness, it should be one of the closest.
A few questions on your equipment. Firstly, you're from Michael is asking, you're remotely controlling your Spanish telescope from Chiswick. How reliable is your system?
Very reliable. The setup in Spain is very good. It's quite a large site there. I think they have about 70 telescopes. So they've refined and matured the setup there. We have high-speed fiber optic broadband, and it's fine. It occasionally goes down. Occasionally you get power going down. But the whole thing's been designed to be fail-safe. I can have the telescope running in the middle of the night. The power can go down. The clouds could come over. It could start raining. The internet could go down, and the whole thing will close itself down safely. And even if my PC crashes, it'll still be safe. So it's pretty reliable.
And following on from that, what sort of photographic gear works for you? I guess he's asking sort of cameras and photo wheels and things you use.
The cameras mine are all CCD cameras. They are the two cameras I've got in Spain are QSI 6120s, I use Astrodon filters.
Okay. Steve asks, why does S2 in the spectrum rule out a planetary nebula? Both M27 and M57 show some S2 emission.
That's a tricky one. I'm not sure that my knowledge of astrophysics is good enough to answer that. I think it would put it in doubt, but I think it's possible to have some S2 emission, but generally you don't get sulfur thrown out from the outer shell of a star, is my understanding. But I'm sure that there are far more knowledgeable people around than I am who could answer that more accurately.
And processing software, what do you use for?
I use CCD stack for stacking, and simple old basic Photoshop for processing. That's all.
Have you encountered any problems with the Starlink satellite networks causing problems for your imaging?
No, I haven't. Yes, I mean, there are always satellites going over. The advantage of Spain is I don't have aircraft going over, which I have in Chiswick. Yeah, it's normal to find satellite trails on subframes, sometimes several satellite trails if it's a 30-minute exposure. But I take large numbers of exposures, and so you can process those out quite easily.
And a question from Peter is asking, he's a remote user at the same site. He's asking, do you use two telescopes to half the exposure duration for a particular color, or do you gather two colors at the same time?
I tend to use the two telescopes just to get more data. I would not halve the exposure because I've got two telescopes. So if I need a 30-minute exposure, I will do that on both telescopes. So it just reduces the amount of, it halves the amount of time, elapsed time, in order to get the data I need.
But with the same filter, or with, do you do different filters?
Well, no, I mean, that varies. Sometimes if I need, for example, masses and masses of O3 data, I need 20 hours of it, then I might have both telescopes using the same filter. On other occasions, I might have one doing luminance and another doing RGB, or I mean, it really depends on what I need and what more data I think I need. But effectively, I can use either telescope. They've both got a complete filter set, so it's driven by whatever I need most. I tend to, for new discoveries, the critical thing is there any oxygen O3 data there? The HA is likely to be fairly bright, and that will already be discovered. What I have found is if I don't find any oxygen within 20 hours of imaging, then there's probably nothing there. So I would rather have both telescopes doing oxygen data gathering to see if there is something there before I go and spend a lot of time doing anything else.
Okay. And just a final one there from Steve, just thanking you for your presentation. It's great to see what amateurs can still do. So yeah, thanks for that, Steve. Quite agree. Great. That does it for the Q&As, I think. I don't think there's anything in the chats either on here or on YouTube. I think YouTube is maybe still a little bit far behind us, unfortunately. But yes, thanks very much for that, Peter. That was an excellent talk, and hope it might inspire a few more people to take up either hunting for potential planetary nebulae and our imaging candidates that might be found along the way. So thanks very much, Peter. That's been excellent. If we're moving along now, our thanks for all your patience. We're a little bit behind schedule. Apologies for that. If you want to go off and have a cup of tea or whatever and drop out, and it's just going to be my boring bit at the end, really. I was just going to do a little short presentation on the review of the year. Hopefully that's is coming up for people now. So it has been a strange year, really. We were due to have our deep sky section meeting in Sheffield last year in March, but we did have to cancel that, unfortunately. Just to update on section personnel, Assistant Director is Jonathan Blake, General Advisor Ron Arbour, Double Star Advisors John McHugh. So if you're interested in doing any sorts of double star observing, you can get in touch with John. Nick Hewitt's our Variable Nebula Coordinator, so he gathers all the observations of variable nebula together as well. Supernova Patrol is still manned by Guy Hurst. Many thanks to Guy for continuing in that role. I don't think we've had any amateur supernova discoveries in the UK in the past year. It's probably been quite a while since we've had any, but we live in hope, and there still are a few bright supernovas appearing, and it's nice to see those being observed by members when they occur. Website galleries, many thanks to Paul Downing who looks after all of those. That's changing a little bit with the new image galleries, but we'll continue with those, and great thanks to Paul for helping out with those. I've made Nick James redundant, sort of thing, as remote imaging advisor. We discussed this, and since remote imaging is a bit more ubiquitous these days, a specific role within the section didn't really seem appropriate, and so although I'm sure he's not had any questions about remote imaging through the section for many years, we agreed that that's probably not a role that we need to have anymore. Section membership at the moment amounts to 199, so there's 199 nominated people in the section, which has been growing over the past couple of years. I think we were about 160 or something, a couple of years ago. Have issued the Deep Sky section newsletter for 2019 at the end of last year, so we almost caught up with that. I'm planning on getting a 2021 out fairly soon, so look out for that. And then we'll try and get into a more regular, maybe 6-monthly cycle. But contributions and material for that's always welcome. We'd really like some articles for that, and it would be great if anyone could send anything in on that. Many thanks to those who have contributed to the journal's Observers Forum. We've been trying to keep a steady stream of deep sky articles in the Observers Forum. So many thanks to Owen Brazell, Stuart Moore, Nick Hewitt, who've contributed to the Observers Forum over the past couple of years in the journal. The website continues to be developed. Had a little bit of a restructure around variable nebulae recently, and there will be some new pages around globular clusters coming up fairly soon. Been issuing these monthly deep sky updates, which some months are fairly brief and some months are a bit more extensive depending on what's happening. We've also been extending the sort of historical aspects. So in the document downloads area, we've now got a series of folders which have all of the historical newsletters that were produced by the section that we have had hard copies for. So this goes back to when the section was formed back in 1982. So we've got newsletters from there all the way through to now. There are some gaps, I think, just where there weren't newsletters produced, but I think we have got them all there. And many thanks to Owen Brazell who scanned his collection of those for me, and we posted those up a little while back. We've had the new members, members albums, members images website set up in the last month or two, or towards the end of last year, and those are being becoming increasingly popular with members to post to. And there are many interesting things that you can do with this, the new site. And here's an image from Martina McGovern of the Leo triplet. But one of the great things about this is the ability to tag the objects within the image, and also for the plate solving capabilities. So Dominic Ford wrote this software, and it will use astrometry.net type of software to plate solve the images, and then you can overlay deep sky objects and grids and all sorts of interesting things. It's also useful because you will normally be able to capture what equipment you've used to make the images and things, so that's always helpful, and sometimes gets lost in the email communications. And yeah, so here it is with the plate solving overlays. Let's see what objects are actually on the image. Another nice thing about Dominic's software is it lets you do a map of observed objects. So this is observed objects in the past year or so on the sky, which have been classified as deep sky. It's quite possible that some of these objects aren't actually deep sky objects, and the classification got a little bit awry. Something we're going to try and fix up, but some of these are obviously just large wide field images of like Orion across here and Taurus and areas up here, which may actually be planetary conjunctions and things. But you can get a bit of an indication of a sort of like a heat map by looking at these images, these search displays. Just to quickly go through a few observations through the year. Variable Nebula team has been quite active this year actually, and it's been interesting to see the Variable Nebula images that have been coming through. Grant Privet in addition has been made a proposal to the Europlanet, which is a funded organisation for getting telescope time on professional telescopes, and he's successfully got us some time on the University of Kent Beacon Observatory, which is a 17-inch plane wave for doing some observations of fainter variable nebulae. And it's been great to see a number come in. Richard Sargent has recently started getting a bit more active as well. Here's Richard's image of Heinz variable nebula. And this is Gaio Badagian's nebula by Mike Harlow. That was interesting because it seemed to have switched off completely middle of last year, and then just in the last couple of months has started to just come back into view again. So we can just see this small plume of nebulosity again coming out of PV Ceph. And this is Grant's image of Borisov's nebula. I'm quite sure where it is. I think it's just a little bit here in the middle, and this was using the plane wave. Also had a color image of Hubble's variable nebula. It's just a bit unusual to get color images of variable nebula coming in. This was from Randy Tatum in Arizona, which is just using a color DSLR to take an image. So Dennis Pazinski has also been sending in some deep sky images. Many thanks to Dennis for that. Interesting that was he's our furthest north observer, I think. So and it's a remarkable amount of clear skies he gets from fairly far north of Scotland. Also in Scotland, Ian Cartwright, he's on the Ayrshire in the southwest of Scotland, has also been producing some remarkably nice images using Nikon DSLRs and Newtonian telescope. Paul Brierley has produced a lovely elephant trunk nebula. Nick James made this interesting mosaic of M33 using his automated telescopes in his back garden and doing auto mosaicing of it. So there's a couple of boundary lines visible. It's a really interesting high resolution image when you see it full scale. David Finnegan's been continuing with Planetary Nebula imaging from Hale Zone in the West Midlands. Again, using I think it's a 10-inch Schmidt Cassegrain, so it's getting quite nice resolution of these. Dale Holt's been continuing with his live sketching of objects, specialising mostly in galaxies and galaxy clusters. Had some nice results since the Christmas, since the second half of last year after the summer break. David Davies, also around Cambridge, has been producing some remarkable fine astrophotography types of images. Particularly like this galaxy in Leo Minor. Again, it's one of those which gets out to be a bit under displayed. And Neil Webster has been also continuing to produce lots of nice images. Many of these are available on the members pages. Some of these have just been sent direct to me. And Paul Whitmarsh has used one of the nice new William Optics Red Cat telescopes to get this nice wide field view. And just to show that comets do still get in the way of deep sky objects, here's a rather nice view of galaxies around Fornax and Eridanus, and unfortunately there's this big bright comet which got in the way of all of the galaxies. Nice image taken by Martin Moberly using one of the eye telescopes. So many thanks to everyone who's submitted observations, either sent them direct to me or sent them via the members pages. I look at the members pages all the time to see what's coming in. Looking forward, I've got a few plans for the section. Just looking forward. I want to do a new do some reviews of the programs, the observing programs. The Variable Nebula program, of course, is well established. Thanks to Nick Hewitt for that. There's a new globular cluster program in the works. Much of this has been authored by Paul Leyland, so thanks to Paul for that if he's viewing today. But I'd like to review some of the other programs which we still have kept as historical programs. But I'd also like to get any new program ideas that any members might have. And if you've got any good ideas for programs or would like to coordinate one of the other programs, if you want to volunteer to do that, that would be great. And another thing that I'd like to do over the next year is to start uploading some of the section archives to the image libraries. We've got a lot of archival data, so there's lots of images which Stuart had when he was director, which is sitting on a hard drive of mine at the moment. So I'd quite like to make those available to a wider audience, and hopefully will become useful for other people who want to look back at what people have imaged in the past. And then there's also some historical images, photographs mainly, slides, which would be quite nice to scan and bring online as well. But what I'd really like to know is, what do you want from the section, really? I've been sending out the monthly email updates, so I hope you find those useful. If you do, it would be great to let you know that you find them useful. If you don't find them useful, it would also be nice to know that. I'd be able to open up the email list so that it could allow you to post as well, if you think that would be useful. And maybe have more discussions around topics. So if you think that would be a good thing to do, then perhaps you could let me know. I've also been thinking about whether we should have deep sky challenges or objects of the month. I know that we already have the Observers Challenge each month on the main BAA website, but we could do something specific for deep sky if people would be interested in looking at those and following up on them. But if you have any thoughts or ideas, please do let me know. So finally, a deep sky section meeting in 2022. I certainly hope we'll be able to have one where we all meet in person. I think I actually mistyped that first of all, and it said hopefully in Preston, but I'm sure it won't be in Preston, but it will hopefully be in person. So I'm looking forward to that, and getting back to something more akin to normality will be great. So just like to quickly thank everyone for being here today. Just also like to thank John and Peter for their presentations, and Andy for his manning of the IT. If anyone has got any questions or contributions, or would like to raise anything, then please do post them up. Let me just have a quick look at the Q&A. Daryl says he likes the challenges, even though as a visual observer he's surrounded by LED streetlights. And Owen says, with the rise of an EAA, so that's electronically assisted astronomy, including by me, do this section have any plans to work on that? It's an interesting idea, actually. I was thinking about that a little bit, and it would be nice to embrace EAA. Whatever that might be. I know lots of people have different ideas about what EAA means, and Cloudy Nights has a rather strict definition of it, and Stargazer's Lounge has a more relaxed view on that. But certainly it seems to be a growing thing. I think I talked a bit about it in my presidential address a couple of years ago. So yeah, I certainly like to develop that more within the section. Michael asked EAA is electronically assisted astronomy. Basically, it's using digital cameras, CCD cameras, to image directly at the telescope, but most of the observing is actually done sort of live at the telescope, rather than gathering data and then processing it afterwards once you've done all of the observations. So there are tools for live capturing of those images, and live stacking, as it's called. So you see the images build in front of you. It's a bit like the sort of thing that Dale does with his video astronomy. Builds up the images, he views it on the monitor, and then he actually sketches those images and gets those fleeting glances of things which you don't necessarily get in a long-term observation. So that covers everything that's come up in the Q&A. I'm always happy to for anyone to get in touch with me at any time. Just send me email either from the to my home email address or via the BAA website. Always good to hear people's views on things. Right. Well, thanks very much, everyone. I think we'll wrap things up there. I'm sure Andy wants to put his feet up for the rest of the day, having manfully done all the IT for the session today. Many thanks to Andy for that. Many thanks to everyone that's attended today. I think we've had a good turnout. We had something like 80 something at its peak, and on Zoom, and I think we had something like 20 or 30 on YouTube viewing. So that's been a pretty good result, I think. So thanks very much for your attendance. I hope you enjoyed the meeting, and look forward to meeting you all properly at some time in the future. Okay, bye for now.